We present AnyFlow, arbitrary scale optical flow with implicit neural representation. To apply optical flow in practice, it is required to perform image downsampling in order to reduce computational costs. AnyFlow is a new optical flow network that is robust to image resolution. The key insight behind AnyFlow is the use of implicit neural representation for flow estimation. Owing to its continuous representation, AnyFlow can estimate optical flow in an arbitrary scale depending on our target resolution. Therefore, AnyFlow can restore optical flow in the original size from the downsampled low-resolution images with clear boundaries. As a result, AnyFlow shows more accurate predictions, especially on object boundaries and small objects from low-resolution images. AnyFlow is based on the Raft framework, which consists of feature extraction, correlation volumes, and GRU update. In the feature extraction stage, a single shared feature encoder extracts multiple scales of feature maps from the two input images respectively. Subsequently, the extracted feature maps are used to compute the correlation volumes, which are basically the dot product between every feature vector from the first frame and z from the second frame. In the iterative GRU update stage, the computed correlation values are fed into the GRU module. Then, the GRU module estimates the residual flow, denoted as delta F, which is accumulated by every GRU iteration. Based on this framework, we propose 3 additional modules to make the network more robust to low-resolution images. The first one is the neural implicit flow upsampler, which upsamples optical flow into arbitrary sizes using an MLP. After the GRU operation, we can gather 2D feature map and the estimated optical flow in the quartz resolution. Here, the feature map corresponds to the hidden state of the GRU module. In order to upsample optical flow, we represent each pixel in the upsampled flow as a convex combination of 3x3 neighborhoods in the quartz flow. Therefore, we multiply the convex weights W by the neighborhoods of the quarry point XQ in the quartz flow to compute the flow of the quarry point in the upsampled flow. The convex weights are computed as the output from an MLP function f theta. F theta takes as input a concatenation of the feature vector sampled from the 2D feature map and the relative position. The sampled feature vector, denoted as Z star, is the nearest feature vector from XQ on the feature map M. The relative position is the difference between the coordinate of Z star and the quarry point XQ. In this way, we can upsample optical flow into any desired resolution by adjusting the number of quarry points. The second method is the multi-scale feature warping. To capture small objects well, high-resolution information is required. However, the complexity of the correlation volumes limits the use of high-resolution feature maps. To address this issue, we design multi-scale feature warping to compute a partial cost volume and effectively utilize high-resolution feature maps. The key technique here is to warp the high-resolution feature maps extracted from the feature encoder by the estimated optical flow. In order to warp the various sizes of feature maps, we leverage the implicit upsampler, which upsamples the estimated flow into the size of each feature map. In this way, we can estimate the residual flow by utilizing high-resolution information by circumventing the memory intensity of the correlation volumes. The third method is dynamic lookup. Raft defines correlation lookup operation to generate feature maps by indexing the correlation volumes. However, the lookup operation is fixed and shared across every pixel. Instead, we propose dynamic lookup to predict the lookup range depending on the input images and each pixel. To be specific, the network predicts lookup range R as the pixel-wise output, which is updated by the GRU iteration. In this way, we can make the network generalize well on diverse shapes of inputs and ranges of motions. for the experiments, we used the MPI scintille and the Kitty datasets. The MPI scintille dataset consists of video sequences of synthetic animations which are rendered with naturalistic effects. The Kitty dataset is a real-world dataset captured by autonomous driving cars. In this table, we quantitatively compare robustness to image downsampling with the recent methods. We used end-to-end point error as the evaluation metric, which computes the L2 distance between predictions and ground truths. During the inference, we feed input to the network as downsampled images by multiple scales from 50% to 90%. When AnyFlow takes downsampled images, it shows only 1% of degradation up to 80% downsampling on scintille dataset. Also, when taking input as 50% downsampled images, it is still better than the original results of the baseline raft. On the other hand, the other methods show severe accuracy drop comparing to ours. In this figure, we visualize the close-up images at various downscale ratios as denoted by the numbers. As shown in the figure, the recent methods lose ability to capture small objects, and they do not show consistent results with different scale factors. On the other hand, AnyFlow shows consistent performance and captures small objects well with any sizes of images. Also, we compare the results of upsampling the flow into higher resolutions by different methods. The left one is the result of our proposed implicit upsampler, the middle one is that of bicubic interpolation, and the right one is computed with the recent super resolution method. As shown in the figures, the interpolation and the super resolution generate artifacts. On the other hand, our methods perform upsamplings with less artifacts and accurate boundaries. To summarize, we proposed AnyFlow and demonstrated strong performance on diverse input resolutions. In addition, we adopted implicit neural representation to generate output in arbitrary scales. AnyFlow is the first optical flow method to be designed for low-resolution images and for tiny objects. Thank you for listening.